Open almost any biology textbook, and you will see a picture of a cell that looks like a soup bowl. The liquid inside is treated as an empty, passive bathtub. The text tells us that all the heavy lifting is done by complex molecular machinery, DNA folding, proteins unzipping, and enzymes acting as tiny motors to keep you alive. But that picture ignores the actual environment those machines operate in. A cell's interior is a microscopic hurricane of thermal energy, with molecules violently smashing into each other trillions of times per second. This graphic illustrates what physicists call the KT paradox. KT represents the baseline thermal noise of that molecular hurricane. Notice how the massive amplitude of this chaotic background heat completely engulfs the tiny, fragile waveforms of biological signals trying to pass through it. If you drop a delicate signal into that much random noise, it gets obliterated. Under standard thermodynamic models, the highly organized communication required to keep a cell alive simply shouldn't be able to happen. The math only balances if we treat cellular water as an active thermodynamic engine, a system that harvests the surrounding chaos to build internal order. In physics, we call this a super-Q resonant system. Unlike a standard machine that drains a battery to do work, a super-Q system draws in the random heat of its environment and converts it directly into a synchronized frequency. This diagram maps the engine's core mechanism, the tripole architecture. It requires three parts: an entropy source of raw chaotic energy, squeezed through a directional valve called a mediator. Out the other side, the energy emerges completely structured into a coherent sink. In biological systems, the liquid water surrounding the cell provides that first step. The random thermal collisions in the bulk water act as an infinite entropy source, feeding raw fuel to the engine. To turn that raw heat into usable structure, the engine needs a valve, a mechanism that allows energy to flow in but prevents it from scrambling back into chaos. The secret to that valve lies in the precise geometry of a single water molecule. When two hydrogen atoms bond to an oxygen atom, they lock in at an angle of exactly 104.5 degrees. Overlapping that molecule with a perfect pentagon with an internal angle of 108 degrees shows the water molecule is off by 3.2%. When millions pack together, this geometric mismatch creates topological frustration. They constantly try to form five-sided rings, but the angles don't fit. The network flexes, snaps, and reconfigures without ever settling. Because of this permanent tension, the liquid can neither lock solid into perfect ice crystals nor scatter completely into random noise. That exact state of perpetual, vibrating frustration is what forms the mediator valve. When ambient infrared radiation from the environment hits this frustrated boundary layer, the network absorbs the energy to relieve the tension. The energy forces a massive structural shift. Instead of vibrating randomly, millions of adjacent molecules suddenly lock into a synchronized collective oscillation. Physicists call these synchronized regions coherence domains. By vibrating together, the molecules act as a giant microscopic antenna. This chart illustrates the result. The flat line at the bottom shows the baseline thermal efficiency of standard molecules. But inside a coherence domain, the collective interaction energy scales exponentially, generating a quality factor 3,000 times higher than the passive thermal limit. The geometric valve has successfully taken weak isotropic heat and converted it into a highly focused, self-trapped electromagnetic field. All of this math takes place at the quantum and molecular scales. But this thermodynamic engine leaves a very clear signature that we can see with our own eyes in a standard laboratory. When bulk water encounters a water-loving surface, it spontaneously reorganizes into what researchers call exclusion-zone, or EZ, water. The molecules align into massive hexagonal sheets, pushing out particles and leaving a distinct crystal-clear layer. This exclusion zone is the physical embodiment of the coherence sink we tracked in the tripole model. It separates electrical charge, filters out impurities, and stores energy. We don't have to guess if the geometric anomaly of the water molecule can do real work. We can put it in a beaker, shine infrared light on it, and watch the organized exclusion zone grow in real time. Which brings us back to the human scale and that original textbook drawing of a biological cell. Cell membranes act as the nucleation point for this process. These hydrophilic surfaces are specifically positioned to organize raw water molecules into vast layers of exclusion zone water on both sides. Every cell in your body operates as a nested super-Q cavity. Its internal geometry is precisely arranged to capture thermal noise, feed it through the mediator of the water molecule, and sustain the electromagnetic fields that power your biology. A moment of wonder. Biological life didn't accidentally learn to survive in the chaos of the molecular world. Life is the inevitable biological engine that emerges when a tiny geometric flaw forces the raw heat of the universe into coherent order.